I'm out today, and I was planning yesterday on teaching you this new section, and it just didn't happen. So I thought I'd record a lesson today and play it for you, and that way you could take some notes and then try some problems. So we're going to be looking at a new section, section 4.5, which is titled Applied Optimization Problems. So whenever we do these optimization problems, we're trying to optimize something that is usually find either a minimum or a maximum of something. So for example, we might try and find the dimensions of a rectangle that have, say, a fixed perimeter, which means, let's say that you have a certain amount of fencing you want to use to encircle the outside, but you want to maximize the area. Or what is the least expensive shape for a cylindrical can? Or what is the size of the most profitable production run? Calculus can answer all those questions, and we're going to start tackling some of them. The first example we're going to do is fabricating an open top box. So if you kind of imagine a sheet of paper, and we're going to fold up the sides, fold up all four sides, and cut out the corners to make a box. And that box is going to be an open top. It's not going to have a lid. So our first example is going to be a piece of cardboard that is 12 inches by 12 inches. Again, we're going to cut out the corners. We're going to cut out the corners and fold up the sides. And what I want to know is, what size should our cutout corners be in order to maximize the amount that the box can hold? So once we've drawn the picture, I'm going to label as much as I know. I know that each side is 12 inches, and I don't know the size of the cutout, so I'm just going to leave them as side X, because we don't know how much we're cutting out. I do know we're trying to maximize volume, so I'm going to try and write a volume equation for my box. And to find the volume of a open top box, you can take the length times the width times the height. In our case, two of those dimensions are going to be the same because they're both 12 inches. So if you want to think of it this way, the length and the width are going to be the same at 12. The height is actually going to be X, because once you fold up the sides of your cutout, that will be the height. Also, we need to think about the length and the width. It's not really going to be 12. It's going to be something less than that, because we're going to be taking the 12 inches that we started with and cutting out the corners. We're going to be cutting out those corners of side length X, which means that each one of these dimensions is 12 minus 2x, and we have two of them, so we're going to square that, and that's our length times our width. The height of our box is going to be just a height of X. So right now we have a volume equation that represents the volume at different amounts of side square cutouts from the corners. Before we go any further, think about what the domain might be. So think about the possible values for x. So smallest value for x, I think, would be 0. The largest value can't be 12, because if the largest value is 12, then we would have a negative length of a side. So if you think about it, the largest x value could really be a 6, because if I substitute 6 in for x, then one of my dimensions would really be 0. I'd have a height of 0. So my domain, I would say, is 0 less than x, which is less than 6. We're not equal to, because if we were, then we wouldn't actually have a box at all. We'd just have a flat piece of cardboard or sheet of paper. The next thing I would do is I would graph this. So I graph that, and hopefully it's maybe even a little bit clearer why the domain is 0 to 6. On the y-axis we have the volume. On the x-axis we have these squares of the side that are cut out. So if you check out the x-axis, we hit a 0 at 0 and at 6. And somewhere in there is going to be a maximum volume. It looks like roughly at 2. So we'll go through some of the calculus and the algebra, and we'll see if we actually get that same result. So what we're really trying to find here is a local maximum. So we're going to start by finding the derivative. And it might be helpful in this case to actually expand out the 12 minus 2x quantity squared times x before we find the derivative. So that's our original volume equation expanded. If we find the derivative, we'll get 144 minus 96x plus 12x squared. And we're going to want to set that equal to 0 and solve. So I know we could factor out a 12. And that factors further into 2 minus x and 6 minus x. So our critical points are going to occur at 2 and 6, but again, 6 isn't in our domain. So the only point to test is at 2. We're also going to need to check our endpoints to find if we're looking for absolute, really, it's the absolute maximum. So we're going to look at the volume at 0, the volume at 2 at our critical point, and the volume at 6. Our volume at 0 should be 0, volume at 6 should also be 0, and you can get that from just substituting 0n or 6n to your original volume equation, or by also looking at the graph. It looks like the volumes will be 0 at an x value of 0 and x value of 6. A volume of 2 will result, an x value of 2 results in a volume of 128, which means that this is going to have a maximum volume of 128 inches cubed, which means the squares, the cutout squares, should be 2 inches on a side. So let's kind of review the strategy there. The first thing we did is we had to read the problem. And this might take you maybe 2 or 3 reads in order to really understand what they're asking in the problem. That's okay. Think about what's given. Think about what's unknown. We knew what was given is that side lengths were 12 inches. We knew the unknown was, well, what are the size of the cutouts to make that height? Second step, you're going to want to draw a picture and label any part that may be important in the problem. So you might have to introduce some variables. And after you have your picture, you understand the problem, you have your variables, then you're going to want to write an equation for that unknown. Lastly, test your critical points and the endpoints in the domain to come up with your answer. Let's do a second example. And if at any point you need to maybe see this again, maybe Coach Winfield can stop this and then rewind it a little bit if need be. So let's say we want to design an efficient cylindrical can